Module 7.2, Radian Measure and Graphs of Trig Functions. This is section 6.1 and 6.3 in your book. 7.2 opener. In this section we're going to cover the radian measure as opposed to degree measure, and then we're going to look at the graphs of trig functions. For the most part, radian measure is the most commonly used measure. We don't really use degree measure that much, especially in this class. We're not going to use it as much now. And the graphs of trig functions are going to be used heavily in the remainder of this course, so you definitely need to know the basic graphs of trig functions. Just like you know what the graph of x squared looks like, the graph of x cubed looks like, the graph of the absolute value of x looks like, the graph of square root of x looks like, graph of log of x, what that looks like, graph of e to the x, what that looks like. All right. The basic shapes, you need to know the basic shapes for the trig functions, because we're going to start using combinations of all this. You're going to need to know how to convert between degrees and radians. Again, for the most part, we'll be using radians, so if you're given degrees, you need to know how to go to radians. Everything you have memorized so far about degree measure, you're going to have to memorize again about the radian measure. So if you know what sine of 30 is, you should know that's 1/2. You should also know what sine of pi over 6 is once we get to that. It turns out to be the same, 1/2. You should be able to quickly sketch a graph of the sine and cosine functions, and we'll look at that in a second. Definition for the radian measure. Suppose we have an angle in standard position with a ray extending through a circle centered at the origin. So we have a center at the origin and a ray extending. Let's imagine we have a circle there. Okay. When the length, and this ray is moving in the counterclockwise direction, when the length of the ray is equal to the arc length, in other words, when this length is equal to how much it's extending on the arc length, then we say that the angle has a measure of 1 radian when those two things are equal. So let's call this length r. After a certain time, when this thing is equal to r also, in other words, we have r, and r there, then that measure right there, that theta, that angle, is a measure of 1 radian. Okay. And what's interesting about that is that it doesn't matter how large that circle is. If we have a smaller r, when that r is equal to the arc length here, that theta is still the same, still equal to 1. Whenever you travel another r, that theta will equal 2, etc. Whenever you travel another r, that theta will equal 3. In general, the formula theta is equal to s over r gives the relationship between the angle, the arc length, and the radius. In other words, if you have some theta, some r, and some arc length, s, then this formula always has to be true. Theta is equal to the arc length over the radius. When the radius is equal to 1, that means that theta and s, the arc length, have to be equal. Right? When this bottom part right here is 1, then this says theta is equal to s. When theta is equal to 2 pi, and s is equal to 1, then that means the arc length is equal to 2 pi. This turns out to be the same as the circumference of a circle. Remember, the circumference of a circle was 2 pi r. In other words, the arc length when it's all the way around. So what we found is that all the way around a circle is equal to 2 pi. which means that 2 pi is the equivalent of 360 degrees. And taking half of that, that also means that 1 pi is equal to about 180 degrees, is equal to 180 degrees. Remember, pi is just a number, it's about 3.141, etc. So because of the way that ratios work, this gives you an easy way to convert between degrees and radians. If you want to convert 30 degrees to radians, all you have to do is divide out the degrees. So if you divide by 180 degrees and multiply by pi, you'll get your answer in radians. Right? This is 1 over 6 pi, or pi over 6 radians. Likewise for 45 degrees, divide by 180, multiply by pi. Turns out to be pi over 4, because 45 goes into 180 4 times. Likewise for 60 degrees, 60 divided by 180 times pi. That's pi over 3, because 60 goes into 180 3 times, so it's pi over 3 radians. Likewise, if you want to convert radians, pi over 2, to degrees, you do the opposite. You multiply by pi. You divide by pi. You divide out the radians, essentially, and you multiply by the degrees. So you divide by pi, and you multiply by 180. So here the pi's cancel. I'm left with 180 over 2, which is 90 degrees. So pi over 2 radians is the same thing as a right angle. Pi over 2 is the same thing as 90 degrees. About 5 pi over 3. Divide by pi, multiply by 180. The pi's cancel. I'm left with 180 times 5 over 3. This is in degrees now. About 3 over 2. 3 over 2 radians, right? Still, we're going to divide by pi, even though there's not a pi there. Divide by pi and multiply by 180. So it'll be 3 times 180, or you can do 180 divided by 2 is 90. So 3 times 90 over pi, or 270 over pi degrees. Right? So just because you have pi there doesn't mean you have radians. This was our original radian amount, 3 over 2. Graphs of trig functions. A periodic function is a function with the following property. F of x is equal to f of x plus n times p, where p is your period and n is just an integer. Like, remember, whole numbers that are positive or negative. In other words, the function f of x is equal to f of x after some number of times, after some period, 1 period or 2 periods or 3 periods. It equals the same value. Because of our definitions of sine and cosine, sine and cosine repeat themselves after values greater than 2 pi. Remember that we defined sine and cosine as these ratios of these triangles, right, depending on whatever angle we're looking at. And we said that after 360 degrees, or after 2 pi, we get the same triangle over and over again. So after every 2 pi, since we end up at the same triangle, we should have the same values for sine and cosine. So what we have is that sine of x is equal to sine of x after 2 pi, or after 2 times 2 pi, or after 2 times 3 pi, after that many number of rotations. And same thing for cosine. Now if we wanted to take sine of x as a function, y is equal to sine of x, and we wanted to plot this function on the graph and look at its graph, we could try the same thing. We just look at x and y values like we've done before, right? And we should look at values that we know the values for, angles that we know the values for, like pi over 3. Pi over 3 is the same thing as 60 degrees. pi over 2 is the same thing as 45 degrees. Sorry, 90 degrees. Pi is the same thing as 180 degrees. 3 pi over 2 is the same thing as 270 degrees. And 2 pi is the same thing as 360 degrees. Right? And you'll get used to these. The more you convert these over yourself, the more you'll get used to them. But also try to memorize them. So let's try to graph some points here for sine of x. Y is equal to sine of x. We have x values and y values here. X, y. And let's start with 0. Sine of 0 was what? Sine of 0 was 0. So 0, 0. What about sine of, and let's try pi over 6. Pi over 6 is the same thing as 30 degrees. That was 1/2. So let's say that's pi over 6 there. Let's graph it from 0 to 2 pi, since we know after 2 pi it repeats. So there's 0 to 2 pi, halfway there is pi, halfway there is pi over 2. Okay. So at pi over 6 we get 1/2. We know that sine also has to be between -1 and 1. Remember that we said that those values are never going to be less than or bigger than -1 and 1. So let's say that's 1. At pi over 6 we get 1/2. Let's look at pi over 2, which was what, 90 degrees? What is sine of 90 or sine of pi over 2? That was 1. So at pi over 2 we reach our highest value. What about sine of pi? Sine of 180. That was back again to 0. What about 3 pi over 2? Or 270 degrees. That was down to -1. Right, remember when we were graphing this, we said 270 degrees is down here somewhere. And the x value is 0, the y value is 1, the r was 1. So sine, since sine is the y coordinate, in that case, was just 1 for 270 degrees. And it's down there, so it's -1. So 3 pi over 2, or 270 degrees, we get -1. And at 2 pi, we get sine of 2 pi. That was all the way back across here. Remember, that's 1, 0. So sine of 2 pi is 0. And if we smooth this out a little bit, and if you try more points, you can try more points on your calculator if you want to. We get that the graph of sine x looks like a little wave function, is what it's sometimes called. And we know repeats after 2 pi, so after 2 pi it's just going to look the same. Right? That would be from 2 pi to 4 pi, because it's every 4 pi that it repeats. Even in this direction, from 0 to -2 pi, it keeps repeating, etc. So really, the only part you have to memorize is from 0 to 2 pi, that little bit. Remember our definition a definition for odd functions from algebra is that if you plug in -x, you should get the negative of f of x. And notice that because sine is symmetric about the origin, in other words, if you were to take this graph of sine and rotate it, keeping the origin, this middle point right here, fixed, if you were to rotate all these values, you would end up with the same looking graph, only negative, the values are different signs. This part right here would coincide to this part down here. This part would coincide with this part. So same values but negative. This negative part right here would now be positive up here. This negative part here would now be positive right here. And that's what this says. If you were to plug in, for example, not sine of pi over 2, because we know sine of pi over 2 is 1, but if we were to plug in sine of, not this value over here, but this value over here, sine of negative pi over 2, we should get negative 1. In other words, down here. And we do. So that's an important property of sine. If you plug in any value, negative value, you should get the same as if you were to plug in the positive value, only the number comes out to be negative. Now we can try the same thing for the graph of cosine. We can plot points x and y values. We're going to try the same one, 0, pi over 6, pi over 6, pi over 2, pi, 3 pi over 2, 2 pi. And you can try you can use your calculator here. Cosine of 0 was 1. Cosine of pi over 6, remember that one was like, this is same as 30 degrees, so that was the same as sine of 60 degrees. Sine of 60 was square root of 3 over 2. Remember, let's do from 0 to 2 pi. So halfway there is pi, halfway there is pi over 2, pi over 6 is down here somewhere. So we get square root of 3 over 2, which is a little bit lower than 1. Cosine of pi over 2 is 0, so now we're down here. Cosine of pi was negative 1. Cosine of 3 pi over 2, that's right there, was 0 again. Cosine of 2 pi was positive 1. So the graph, once we smooth it out a little bit, it looks like that. And it repeats after 2 pi. In either direction. Right. And what we notice here is that cosine is symmetric about the y-axis. In other words, now it's a reflection. If you look at this line down the middle, it's a complete reflection. Whatever's over here on the right side is also on the left side. And that's another definition for an even function. So if we were to try to find cosine of negative pi over 6, it should come out to be not negative, but just the same value. Negative pi over 6 is here. It's the same value, square root of 3 over 2. It's still the same as cosine of pi over 6, which was square root of 3 over 2. So now in this case, even functions are not affected by minus signs. The minus sign doesn't do anything. Okay, so for sine it makes a difference, for cosine it doesn't. Also notice that the graphs are just translations of each other. Sine starts at 0, goes up, backs down, and then to 0 again. Cosine starts at 1, goes down through 0, up to 0 again, and then ends up at 1. But really, cosine is just this part of sine right here. It starts here. And it ends right there. It's just shifted over a little bit. It's shifted over by pi over 2. That little amount right there. But they're almost the same. Okay, so for a function, and that's just something to notice. For a function of the form y is equal to a sine of bx, we call the absolute value of this number a the amplitude. The amplitude is just the distance from the very center to the highest point or the lowest point. And we also say that the function has a period of 2 pi over b, given that b. And the same thing can be said about the cosine function. So for example, for y is equal to negative 3 cosine 2 pi over b, the amplitude would be absolute value of negative 3, or 3. And the period would be 2 pi, just given from the formula here, divided by b. Divided by, b is the number in front of x, so divided by 2 pi, which would give you 1. All that says is that if you were graphing this, you should already know that the distance from the middle to the highest point, or the lowest point, would be 3. And you should know that no matter what this thing looks like, right, it's going to repeat after a period of 1. After this amount on the x-axis is equal to 1. After that, it will repeat. So instead of repeating from 0 to 2 pi, like the cosine originally did, from 0 to 2 pi, this number in front here, this 2 pi, changes the period. Okay, now we're going to practice sketching the graph of negative 2 sine 4x plus 3 over one period. Alright, remember that our period is 2 pi over this number right here, whatever's in front of x, over 4. So pi over 2. Our amplitude is the absolute value of negative 2, which is positive 2. Right. We still don't know what one period is, though. We know it has a length of pi over 2, but we don't know what that interval is. So usually what we do is we look at the graph, the usual period for sine, which is between 0 and 2 pi, and we make an inequality. Then we put in whatever's inside of sine x, 4x in this case, and we solve for x. So solve for x. Here, to solve for x, we need to divide everything by 4. So we're going to divide 0 by 4, which is 0, 4x by 4, which is x, 2 pi by 4 is pi over 2. So we know our period has a length of pi over 2, and it's between 0 and pi over 2. So all we need to do is look at 0 to pi over 2. Let's say that's pi over 2 there. Let's say that's 0. Our amplitude is 2. So usually we would say that goes from negative 1, negative 2, 1, 2. Usually that would mean that we go from negative 2 to 2. But because of this plus 3 here, it means everything is shifted up by 2. So instead of negative 2, we need negative 2 plus 3, which is 1. And instead of 2, we need 2 plus 5. Sorry, 2 plus 3, which is 5. So really, I deleted way too much. Really, what we need to go from is from 1 to 5. So 1, 2, 3, 4, 5. Right, and our amplitude is not starting at, our sketch is not starting at 0 like it normally does, but it's starting at 3. So 0 plus 3. Again, that's what this plus 3 is doing. It's making everything 3 times higher. And our amplitude now is from 0 to 1 is 2, and from 3 to 5, which is still 2. Okay, and now we're just going to sketch the graph of sine. Only be careful with this minus sign here. Instead of saying that the graph of sine looks like, like this, like it normally does, the minus sign is making everything negative. So instead of going up, it's going to start going down, then go back up, and then back down. That's what that minus sign does. So it'll go down to its lowest part, back up to its highest part, and then back down to 0. Okay, so that's a quick sketch of what's going on. Let's just do this on the calculator real quick to make sure that we're doing the right thing. Let's go to y equals. Notice that we're working in radians here. It's pi over 2. There's no degrees, so you need to go to mode and make sure you're still in radians, not in degrees. You're still in radians. Hit y equals. Then we're going to type in our function. Negative 2, not minus 2, negative 2 sine 4x plus 3. And then we're going to go to the window here, and we're going to graph it on our period from 0 to pi over 2 for the x. So the minimum for x is 0. The maximum for x is second pi over 2. The minimum for y is going to be 1. And the maximum for y is going to be 5, right? That was given to us by our amplitude. And then we're going to graph. And let's see if we get the same graph. Yeah, very similar. See, from 1 to 5, it looks exactly the same. All right. Now, let's try to find the arc length intercepted by a central angle of 7 pi over 8 and the radius of 15.7 centimeters. In other words, here, let's draw, whoops, it's not a circle. Let's draw a circle, some center. The radius is 15.7. Let's say this angle right here, 7 pi over 8. It might not be exactly to scale. And we're trying to find the arc length right here. Well, we're going to use our formula, our arc length formula. Theta is equal to S over R. And what are we trying to find? We're trying to find S. So theta is equal to 7 pi over 8. S we don't know. R is 15.7. So this tells us we just need to multiply the 15.7. That would give us that S is equal to 7 pi over 8 times 15.7 times 15.7. Right? And you can do that yourself. All right, you should now be ready to start homework section 7.2.